Welcome everyone. Discussion on channel of the discussion on science. We today talking about is a kind of continuity of the previous lecture, and I will give new ideas, new structure, new methodology to think about it. So previously, what did we do is it's quite clear. We look at the atoms, structure of the atoms, component of the atoms. What would be useful? We'll refer, not maybe too detailed way, but we refer the electron cloud, which related to quantum mechanics, which also related to today's technology, making chips. And today we are actually related to these atoms, related to this atomic interaction. We talk about the force between attraction, repelling force between them. So the guy who observed this attraction and repelling forces is Coulomb. Okay. So we call this is a Coulomb law. There's a force between them. We refer that. There's a force. There's a force too. And this force is a vectoral quantity. I will say it always. What is the vectoral quantity? What do I mean by saying vectoral quantity? It's clearly just that. If I have a two vector, which is f equal to 3i hat. Wait, 3i hat plus 4j hat. F2 equal to 5i hat plus 3j hat. If I ask f plus f2, it does not equal to 7 plus 8, which is 15. This is completely wrong. Please forget it. But most of the students missed that point. If I say, what is f plus f2? You have to look its component like atom. Because force has component too. We look at the most three-dimensional way. We have three different directions. Let's call them I say that to you. J and K. All of them has a magnitude. This means that magnitude, by the way, who don't know this, magnitude, okay, equal to 1, all of them. I am sorry, J hat, and K hat. But it has three different directions. In three-dimensional system, we normally show them like that. I hat, J hat, and K hat. If I give to you f equal to 3i hat plus 4j hat, which means that I have a three component, magnitude of 3 in I hat, magnitude of 4 in j hat. Okay? Then, what was my question? My question is f1, f plus f2. What was the f2? Let's write it down. f2 equal to 5i hat plus, I don't remember. Okay, 3j hat. So, if someone asks to you f plus f2, which is two different vectoral quantity, you just separately add them the same direction, same directionality. So I write initially I plus j, okay, because we have dimension, it could be 0, so 0 times 1 equal to 0, that's fine, but this time 3 plus 5 is 8, 4 plus 3 is 7. Okay, that's the vector equality. That's the what is the meaning of vector equality. Okay, let's go back to Coulomb law. We talk about the interaction between the atoms is quite important. So experimentally, one guy, Coulomb, is observed there's a force between them. So experimentally, this guy also found that this force equal to K Q1 Q2 divided by R square magnitude R, which shows the directionality. Direction. So it is quite important. Direction. What was the directions? Direction was the I hat, J hat, and K hat. So we have different direction. Its magnitude, what was its magnitude? 1. So it does not affect the exact result in a magnitude wise. Generally, when I solve the question, I always write this line. Magnitude of the F times I hat, or J hat, or K hat. It doesn't matter. What was it? Or I plus J hat, or I plus J hat plus K hat. But of course, with different magnitude, with different component. Okay, let's pass through this. So we are talking about the F Coulomb force. We talked the directionality, which is quite important. Now we are talking the K hat. What was the K hat? I'm sorry, what was the K? Constant. Actually, K is 1 over 4 pi epsilon 0. This time, actually, epsilon 0 is really important. What is the epsilon 0? Actually, epsilon 0 gives clues of the light, gives clues to electromagnetic waves, gives clues to almost everything, because it's really related to our imagination, our technology closely. Okay, we take E0. This is called permittivity of free space. I mean, I know this lecture is quite boring, but we have to talk this, we have to discuss them, because some of them maybe will not understand what am I talking about. Or ideal vacuum. Okay. So I say that new terminology, free space, ideal vacuum. What does that mean? Okay, let's imagine the free space. Okay, free space. When I thinking of free space, I always think as an empty blank. Write this in green. Beside this red part, and you imagine that you could be in a just one point, or you could be at the just giant big screen. You could have both of them. It is just about imagination, like the movie of the Inception. That's a good movie, by the way. Imagine that. Based on your imagination, you can change the free space constant. Not change, of course, you cannot change the free space constant, but you can imagine, you can think. It's a kind of a space to think freely. I always thinking like that, but it's, of course, it depends on the context and it depends on the where we use, but we usually, until passing through the really complex, really complicated system, you just think like that. If I have a question to you, just think in free space. You have one particle. For example, if I say to you, there's a particle on free space. Let's call this a point particle in free space. There's another point particle. What is the F between them? Plus. Of course, my first intuition is, okay, they have to repel each other, so they have a same force, magnitude. Their direction is opposite because they repel each other. But you can think you are a kind of observer. You don't have any effect to this system. So, okay, you are just thinking these two particles, not other particles in the universe. If we didn't call this system, we have lots of particles in the world. We have really plus charges, minus charges, neutral particles, attraction between them. So all of them will be crap, will be confused, which means that this causes complication. Complication in the system, complication in the calculation. So free space approach is always useful. I think you should stuck with them. But real definition of free space, we will talk about this. We will talk about it in actually quantum mechanics topics, and about maybe I will refer the electromagnetic waves part 2. So as a result, what was the RF? 1, 5, epsilon 0, Q1, Q2 divided by R square. Hop, directionality, I have to. Okay, vectorial quantity, it has a direction. It has a direction. Okay, D, check. Constant, K. Okay, so that makes sense to all of us. I also want to talk about the unit wise. What was the unit of the F? I don't know your knowledge, but Newton find the F equal to ma, real basic formula, and we will also refer this formula in our calculations, but it's a Newton. That's simple. What is the unit of charge, Q? It is Coulomb. What is the distance between them? So, unit of distance is matter. So I have Newton equal to 1 over 4 pi. I don't know the unit of epsilon 0. Coulomb square divided by matter square. Unit of directionality is nonsense because the magnitude is 1, just a magnitude. Think like that. We have a magnitude. This is magnitude. Okay, unit of 1 over 4 pi is nonsense again. So I have Newton divided by unit of epsilon 0, c square divided by m square. So what is the unit of epsilon 0? Equal to Coulomb square divided by meter square times Newton. We will call this unit of epsilon 0 later in a different way. But now you should know this, and you should stuck with this, and you should check always after your calculation for college students, for high school students. Okay, it's quite important. That's all I want to talk about the Coulomb law. Thank you for listening.